Navigation problems are nice because they provide for an application of both the sine law and the cosine law in the same problem. First, though, we have to clarify a little bit of terminology or notation. With navigation, obviously, we use a compass, and the compass rose is fairly straightforward: north, south, east, and west. But the degrees that we use are a little different than what we would use in mathematics. 0 degrees is north, and 90 degrees is east. So a positive direction is actually clockwise, which is different from the math way of doing things. 180 degrees is therefore south, and 270 degrees is west. And we can describe bearings or headings using these degree measures. So for instance, a bearing of 20 degrees, and typically all 3 digits, in other words, the leading zeros if necessary, are provided, just so that if it's a radio communication and it's possibly garbled, there's no confusion. So if you only hear 2 digits, you're not really sure, have you missed that first digit or not? Whereas if you're always expecting 3 digits, then if you only hear 2, you know you've probably missed the first one. So a bearing of 020, or 20 degrees, that would be equivalent. A different way of saying it would be north 20 degrees east. So where is, on the compass rose, where is a bearing of 20 degrees? You can see that it's generally heading north, but you're heading slightly east. How much east? 20 degrees east. Similarly, a bearing of, let's say, 240 degrees. Where would that be on the compass rose? So 240 degrees is heading southwest. You're generally heading west, but you're heading a little bit south. How much? Well, you're heading west 30 degrees south. I like the 3-digit much better. There's less confusion, I think, and it's easier to explain the direction you're going. So let's take a look at a sample problem, and it's a little wordy. So we've got 2 ships, essentially, leaving port at the same time. The Fighting Irishman leaves port on a bearing of 070 at a speed of 22 kilometers per hour, and the Angel leaves port at the same time on a bearing of 150 degrees at a speed of 25 kilometers per hour. Now, after 10 hours, the Fighting Irishman issues a distress call, and the Angel responds. How far away are the 2 ships? What's the distance between the 2 ships? And what should the Angel's new heading be if it wants to head directly for the Fighting Irishman? And then how long will it take to reach the Fighting Irishman? Now, there's a lot of assumptions for that last question. We're going to assume that the Fighting Irishman stays in place. Maybe it drops an anchor. And we're going to assume that the Angel can proceed at exactly 25 kilometers per hour. Obviously, in reality, there would be all kinds of complicating factors, but let's just keep it straightforward. So the first thing we need is a good diagram, and I'm going to go down onto the next page. The helpful thing to do is just to draw a little compass rose and put on the compass rose the 2 bearings. So we've got a bearing of 70 and a bearing of 150. Now, what's the difference between those 2 bearings? Well, 150 minus 70 is 80 degrees. There's 80 degrees separating those bearings, and that represents the angle between the 2 bearings, between the 2 directions that the boats have sailed off in. And so that is the key for our diagram. We can draw the 2 boats leaving port, one heading on a 70 degree bearing, and I find it helpful to put on a little dot, sort of an extension of the direction it's heading. If it's going at 22 kilometers an hour for 10 hours, it's traveled 220 kilometers. And then we have, on a bearing of 150, we have the Angel traveling for 10 hours at 25 kilometers per hour. So that's traveled 250 kilometers. So you can see certainly that the angel is going to be quite a ways south of the Fighting Irishman. And again, let's just put this extension. You'll see why in a minute. That's on a bearing of 150. So the two boats are a fair ways apart. This angle, remember, is 80 degrees. And if you look at the diagram here, we're looking for this distance, which is the side of the triangle that I've just drawn that is opposite the angle 80 degrees. And we know the two sides on either side of the triangle. So this is a perfect application for the cosine law. We can use the cosine law to find the distance between the two ships. So let's do that. D squared is equal to 220 squared plus 250 squared minus twice the product. I'm running out of room, so I'm going to move this over a little bit. So 2 times 220 times 250 times the cosine of the angle between them, cos 80. And all of this can be punched into the calculator, and then we can take the square root, and we get approximately 303. It rounds to the nearest tenth to 303 kilometers. So the boats are a little over 300 kilometers apart. Now, there's a couple more questions. We want to know if the angel's going to head directly for the Fighting Irishman. On what course? What's its new bearing or new heading? Well, certainly it's going to head almost due north. Even just based on this rough diagram, we can see that it's going to be heading almost due north. The question is, how do we figure out how or why or how much the boat should turn? Now, if you are thinking of the direction that the boat is heading, so right now it's on a bearing of 150, it has to turn to its left, or to the port side. Port is left on a boat and starboard is right. So it's got to execute a turn to the left. And the question is, how much does it need to turn to the left? Well, we can find the answer to that question if we can find this angle here, theta. And the two angles there are supplementary, meaning they add to 180. So if I know theta, then I can figure out the turning angle, and then I can figure out the new bearing. So theta can be figured out because I know all three sides of this triangle now, and therefore I obviously have a matching pair, and I can use the sine law. So let's set up the sine law. We're looking for theta, so we should start with the sine of theta. The sine of theta over the side opposite theta, that's 220, is equal to the sine of 80 over the side opposite 80, which I'm just going to leave as d, because you don't want to use the, in this case it's probably not going to make a big difference, but in general you don't want to use the rounded value that you calculated. You want to use the full precision that you've got on your calculator, and hopefully you've still got it up on your calculator or you've stored it in memory. And so we can solve this for sine theta. Sine theta is equal to 220 sine 80 over d. And therefore, theta is equal to the arc sine of 220 sine 80 over d. And that turns out to be 45.6 degrees. Now, there are instances where you might have to worry about the ambiguous case of the sine law. In this case, we don't, because 220, which is the side opposite theta, is clearly the smallest of the three sides of this triangle. And so there's no worry that we've got potentially an obtuse angle for theta. Of course, there's another option if you did worry that you were dealing with an ambiguous case of the sine law. You could, since you know all three sides of the triangle, you could use the cosine law to find theta. And it seems like a little bit more work initially, but the nice thing is you don't have to worry. There's no ambiguous case of the cosine law. In this case, sine law is fine because we know we're not looking for an angle bigger than 90. All right, so we now know that theta is 45.6 degrees. So what's the turning angle? This turning angle here is 180 minus theta, and that is 134.4 degrees. So in other words, if we were the captain, we could tell the the XO to make a turn to the left or a turn to the port side of 134.4 degrees. And what would our new bearing be? Well, when you make a turn to the left, you're subtracting. If you make a turn to the right, you're essentially going clockwise. Left, you're going counterclockwise. So we need to subtract 134.4 from 150. So the new bearing is 150 minus 134.4 degrees, which turns out to be 15.6 degrees, 015.6. So almost due north, just slightly east of north. Now, how long is it going to take? Well, of course, this was the one that had the most assumptions. The time is simply going to be the distance, and here it's, I think, perfectly okay to use the rounded value. So 303 kilometers, and we're assuming that it can continue at 25 kilometers per hour. And so that turns out to be 12.12 hours, or another way of saying that is 12 hours and 7 minutes. So rescue's on its way, but it's going to take a little while, so we hope the boat is not sinking and they can actually just chill out and wait for their rescue.